Aerodynamics treats of the motion of air or other gases and of the forces acting on solids in motion relative to such air or other gases. Relative wind is the motion of the air with reference to a body. It may be the result of moving air and a stationary body, or still air and a moving body, or both air and body may be moving with reference to the earth. In this case, the relative wind is the algebraic sum of the two motions. An air stream flowing past a flat plate exerts upon it force whose direction depends upon the angle between the plane of the plate and the direction of airflow. This force may be analyzed into component forces, which are called lift and drag. Lift acts at right angles to the relative wind, and drag acts parallel to the relative wind. If the plate is held in a horizontal airstream in this manner, lift is opposed by the weight of the plate, and drag is opposed by the tension on the cord. The acute angle between the relative wind and the face of the plate is called the angle of attack. This angle may have any value from 0 to 90 degrees. It may be either positive or negative. An airfoil is any surface designed to be projected through the air in order to produce a useful dynamic reaction. Airfoils which have been studied and used vary widely in form. This is probably the most common type of airfoil section. Others are convex on their upper surface and concave on the lower, while still others are convex on both surfaces. Relative thickness and curvature of airfoils vary considerably. In general, a line through an airfoil's leading and trailing edges is known as its chord. This is the case with an airfoil having a symmetrical double convex camber. In an airfoil which is convex on its upper surface and concave below, the chord corresponds to the arc of the medium camber. In other airfoils, it is the line of a straight edge brought into contact with the lower surface at 2 points. The acute angle between the chord of an airfoil and the relative wind is known as the angle of attack of the airfoil. A wind tunnel is a device for testing reactions on airfoils and other aerodynamic shapes. It usually consists of a large tube with a constricted throat. A propeller produces airflow, and a honeycomb arrangement is placed at one end to ensure straight airflow. When lift and drag of an airfoil are to be measured, the model is placed in the chamber and supported by wires. One wire runs from the model through the top of the tunnel to a balance arm which is weighted so as to maintain tension and compensate for other forces. From the leading edge of each wing, a wire runs forward in the direction of flight, over pulleys, and down to a bar on a platform type of scale. A second pair of wires runs vertically downward from the wings to another scale. Finally, a wire extends from the tail down to a third scale. In this way, the model is suspended so that the various forces exerted upon it may be measured. The position of the model is observed through sighting scopes. With the air flowing at the desired velocity, drag force is exerted upon these wires. Front lift is measured as the actual lifting force upon these wires. Rear lift as the force upon this wire. Total lift is the sum of front and rear lift. Here is one of the Army's wind tunnels at Wright Field. It is nearly 100 feet in overall length, and the test section is 5 feet in diameter. On the intake end, a huge honeycomb arrangement of metal vanes straightens the airflow. Four electric motors of 400 horsepower each furnish power to turn the fan. Two of the motors are shown here. There are two others inside the tunnel. The fans are 12 feet in diameter and have 12 blades. When driven at a speed of 700 RPM, they produce an airspeed of approximately 200 miles an hour in the tunnel. Wind tunnel tests show how lift and drag vary with the angle of attack of an airfoil. In general, as the angle of attack increases, lift and drag increase up to a point where lift decreases abruptly and drag becomes the principal component. This is known as the stalling angle. From this angle to 90 degrees, drag continues to increase while lift falls off. At 90 degrees, the airfoil acts like a flat plate. It has maximum drag and negligible lift. Wind tunnel tests have also proven that for any given airfoil, lift and drag vary directly with the area of the wing. If the area is doubled, lift and drag are also doubled. Lift and drag vary directly as the square of the velocity of the relative wind. If wind velocity is doubled, lift and drag are multiplied by 4. Lift and drag are directly proportional to the density of the air passing over the airfoil. If air density is doubled, lift and drag are also doubled in value. Expressed as an equation, the lift is equal to a coefficient which is determined by the angle of attack and shape of the airfoil, multiplied by the density of the air, multiplied by the area of the wing, multiplied by the velocity of the wind squared. Drag equals the coefficient, which is determined by the angle of attack and shape of the airfoil, multiplied by the density of the air, multiplied by the area of the wing, multiplied by the velocity of the wind squared. When an airplane is flying horizontally at a constant velocity, the forces acting upon it are in equilibrium. The retarding force, or drag, equals the propelling force, or thrust. The lift must equal the total weight of the airplane. Therefore, the lift and drag equations serve to determine how much weight an airfoil will lift under certain conditions and how much thrust horsepower is required to overcome the total drag of the airplane. The air pressure at various points on an airfoil is measured in order to determine the airfoil's efficiency or its suitability for a given purpose. The measurements are made by building into a model airfoil small copper tubes which are sealed flush with the surface of the model. These tubes extend from the model to a pressure measuring device outside the tunnel. The device is called a manometer. This figure illustrates its principle of operation. The liquid in both the tube and the reservoir will be at the same level as long as the pressure in both tube and reservoir are equal. If by any means, such as this plunger, for example, the pressure in the tube is increased, the liquid is forced into the reservoir, lowering the level in the tube. If pressure in the tube is decreased, the liquid rises above the level of the reservoir. In a device such as this, if the liquid in the tube is subjected to varying pressures, the level will rise above or fall below the level of the liquid in the reservoir as the pressure is decreased or increased. Reading of liquid levels provides an accurate means of determining pressure differences. Additional tubes may be added, each connected to a different value of pressure, and each will indicate that pressure accurately, regardless of pressures in the other tube. Operating on these principles, this bank of manometer tubes is used to determine pressures on an airfoil. Because all tubes are at the same pressure, being exposed to the atmosphere, the levels in the tubes are equal. For test purposes, each manometer tube is connected to a different point on the surface of the airfoil. The majority of these test points are located on the leading edge and upper surface. Relatively few are placed on the lower surface. Of course, this is only a schematic representation of the connection. In actual practice, tubes run from the manometers through an opening and inside of the airfoil to the test point. Atmospheric pressure is usually taken as the reference level. Pressures above atmospheric are called positive. Those below atmospheric are called negative. Actually, these values are pressure differences with reference to the atmospheric pressure. With reference to absolute zero, all pressures are necessarily positive. The model airfoil is placed in the test section of the wind tunnel. It is supported by wires which will transmit its lift and drag forces to the scale. Tubes which connect to the test points are passed through an opening in the tunnel wall and connected to the manometer bank. The manometers, being at equal pressures, are at the same level and are connected to the airfoil. Thus, from each manometer tube, there is a direct connection to a definite point on the surface of the model airfoil. All is now ready for the test, and the engineers leave the tunnel to take up positions where they can observe and measure reactions upon the airfoil. The motors which drive the fans are started. In the tunnel, the model airfoil is subjected to the same conditions which it would encounter in actual flight through a medium of the same density, and pressures along the surfaces are at such values as would be met under flying conditions. The manometer tubes tell the story. Levels fluctuate slightly as minute variations in airspeed or density occur, but the ratios are constant, and the position of the liquid in the tube shows both positive and negative values for the airfoil. The tubes are photographed to assure simultaneous readings of all tubes, and the photograph is used by engineers to plot the pressure curve. In this manner, a diagram is constructed showing the nature and distribution of pressures over both surfaces of the wing section at varying angles of attack. Positive pressures are shown in black, negative in gray. At 0 degrees, there is a small bulb of positive pressure directly upon the leading edge of the wing. Another area of positive pressure encloses the trailing edge and extends forward about 1/4 chord length along the lower surface. Elsewhere, the pressures are negative. As the angle of attack is increased, the positive pressure bulb moves lower down on the leading edge and back along the lower surface of the wing, enclosing the trailing edge. The negative pressure distribution remains fundamentally unchanged, although its values are greatly increased. This diagram indicates that the wing has begun to exert a considerable lift. Increasing the angle of attack still further alters pressure distribution very little, although there is a marked change in values, particularly along the upper surface, where negative pressures are now exerting a powerful lift force. The wing is now approaching its stalling angle. Positive pressures have changed very little in either distribution or value. The negative values, however, have increased somewhat, especially at the leading edge. By further increasing the angle of attack, positive pressures remain practically unchanged in both value and distribution, but the value of negative pressure continues to increase. At this angle of attack, the wing is well past its stalling angle, yet the positive pressures show little indication of change. With the negative pressures, the greatest change is noticed at the leading edge of the wing, where the area continues to expand, and the outline of the pressure area is extremely irregular. Increased angle of attack brings no important change in positive pressure value or distribution, but the negative pressure area is tending to equalize in value over the entire upper surface of the wing. At this angle of attack, the forward protuberance disappears completely, and an area of nearly equal negative pressure blankets the entire upper surface of the wing. Positive pressure areas still show no important change. Another increase in the angle of attack merely results in increased value, distribution remaining almost the same as before. At this final angle, pressures have reached still greater values without any appreciable change in distribution. It might appear from this diagram that at this angle of attack, the uniform pressure distribution over the upper wing surface would be desirable. However, above the stalling angle, the resultant air force acts in such a direction that the drag is its large component. An airfoil at rest in still air is at atmospheric pressure over its entire surface. It has been shown that airfoils derive their lift from the pressure differences acting upon their surfaces. The negative pressure difference upon the upper surface at normal angles of attack being the major component of the lift force. Now let us see what happens to pressure values and distribution at negative angles of attack. From 0 degrees, the angle is decreased to a slight negative value. The positive pressure bulb on the leading edge is practically unchanged. The negative pressure on the upper surface of the wing shows little change. However, the negative pressures along the lower surface begin to increase at the leading edge. Further increases in this area, accompanied by very slight changes in the positive pressure bulb, are the only differences which are readily observable as the angle of attack is further decreased. The angle of attack of an airfoil was shown to be the acute angle between the chord of the airfoil and the relative wind. The angle of attack of the airplane as a whole is the acute angle between the longitudinal axis of the airplane and the relative wind. The difference between these two angles is constant for any given airplane and is called the angle of incidence. Although the angle of attack is constant for any given wind tunnel test, in actual flight, the angle of attack of the airfoil varies with changing attitude and speed of the airplane. Consider the case of an airplane flying horizontally at a small positive angle of attack. As the controls are set to put the airplane into a dive, the angle of attack decreases and the speed increases. Lift decreases, since in this attitude the weight of the airplane is opposed by the resultant of lift and drag. As the flight approaches the vertical, speed increases until the terminal velocity is reached in the so-called vertical dive. In this condition, lift is zero, and the weight of the airplane plus its thrust are opposed by drag alone. In pulling out of the dive, the angle of attack must be increased slowly. During this maneuver, the lift may attain several times the value of the weight. This increase in lift produces acceleration, which in turn produces a curved flight path.